Okay, we are going to do some problems here. Ostensibly, these are surface integral problems, but we want to use divergence theorem. You can always use divergence theorem when you're integrating a vector field over a closed surface, meaning it's the boundary of some solid region. So like a sphere is a boundary of a ball, that type of thing. Okay, so we're going to do number 2. I've already done number 1 and 4. This is going to be number 2. So I'm going to do number 2 and 3. I'm going to do number 2 first. Okay, so S is the surface of the solid bounded by this cylinder and these planes. So this is a cylinder that is on the x-axis, that's along the x-axis, and we have these planes, x equals -1 and x is equal to 2. Okay, so maybe this wouldn't be the most difficult surface integral to do. We would have to split it into 3. We'd have to do one integral on the cylinder, one integral on the plane x is equal to -1, and one on the other plane x is equal to 2. But we're going to do this as a volume integral. So remember, Stokes' theorem says that if you're doing an integral over a closed surface, that's what the loop here means, that it's a surface integral of a vector field over a closed surface. This is equal to the triple integral over the region that is contained by S of the gradient. Not the gradient. The divergent of f, the divergence of f dv. So this is a scalar field, and this is just a normal volume integral. Okay, so for number 2, the divergence of f, okay, this is going to be the derivative of the first component with respect to x, that's 3y squared, plus the derivative of the second component with respect to y, that's 0, plus the derivative of the third component with respect to z, this is 3z squared. Okay, and so the surface integral that we want to compute is going to be the integral over the cylinder, which I'm going to call E, of 3y squared plus 3z squared dv. Now this is over a cylinder, so we should switch this to polar coordinates. So the innermost integral will be the x integral. X will go from -1 to 2. And the outer integrals, well, the projection of this region onto the yz plane is going to be a circle of radius 1. So this is the integral from r is equal to 0 to 1. Theta equals 0 to 2 pi. 3y squared plus 3z squared. So in polar coordinates now, y is going to be r cosine theta. That's like the horizontal axis. Z is the vertical axis, so z is going to be r sine theta. So this is 3r squared. Then we have the r for this. This is the Jacobian for switching to polar coordinates. Then we have dx, dr, d theta. The r here is the thing that you always put when you're switching to polar coordinates or cylindrical coordinates. Okay, this is not a difficult integral to do. The answer is 9 pi over 2. Okay, so just to recap, S was this cylinder. So now we're going to change the surface integral of the vector field over this closed cylinder. So it's important that the cylinder includes these caps. If it doesn't include these caps, x equals -1 and x is equal to 2, then you can't use this right here. Okay, you can only use it if it's a closed surface. Okay. And then we took the divergence of f, which is just the gradient dotted with the vector field. We get the scalar field, we're integrating it over this region. And then going from here to here is just switching from cylindrical or Cartesian coordinates to cylindrical coordinates. So to go from this step to this step, we didn't use divergence theorem. Divergence theorem got us to this integral right here. Switching the cylindrical coordinates got us to this integral right here. Okay, so now I'm going to do problem number 3. Okay, so problem number 3, S is this ellipsoid. Okay, so we can get again, the surface integral that we want to compute is over a closed surface, so we could use divergence theorem. So the function that we're going to be integrating is going to be the divergence of f. So notice that in this case, the divergence of f, well, is going to be the derivative of x e to the y with respect to x. So that's e to the y, plus the derivative of z minus e to the y with respect to y. So that's minus e to the y, plus the derivative of minus xy with respect to z, that's 0. So this is equal to 0. So the divergence of f is equal to 0. So what does this mean? The surface integral of f over this closed surface, over the ellipsoid, by the divergence theorem, this is equal to the volume integral over the ellipsoid. So E is the ellipsoid. S here is like the boundary of the ellipsoid. E is like the solid ellipsoid of the divergence of f. But this is just the triple integral of 0, which is equal to 0. So the answer to this is 0. And I think that would have been a little more complicated if you tried to compute this from the definition. So my bet is that most of the time when you see a surface integral of a vector field over a closed surface, then it's going to be good to use the divergence theorem to compute it. But that only works if you're integrating over a closed surface. If it's not a closed surface, like if this was just the top part of the ellipsoid, you couldn't do it. You can only do it if it's over a closed surface.